Problem 15.96 involves two rods that are connected together. The ADB rod right here connected to a DE rod right there, and we're given several dimensions here, all in millimeters. 200 from there to there, 200 from there to there, 150 over to there, another 150 over to there, 250 over to right here. And we're asked to find what the angular velocities of these two rods are right here, knowing that we have a velocity for B that's to the left of the 360 millimeters per second. And we're also to find what the velocity of point E is as well. Alright. Now here's a sketch of it to find the instantaneous center of rotation. First of all, there's going to be two of them here. There's going to be one for the rod AB. Velocity of A is up or down, so a line perpendicular to that's going to go like this. A line perpendicular to the velocity of B is going to go like that. So where they cross is where the center of rotation is for rod AB here. And so that's point C, and I'm going to call it C1 then for that center of rotation. Then the velocity of D will be perpendicular to this line right here, and since it's part of the DE rod right here, then the velocity of D is perpendicular to a line that goes to its center of rotation. So all we got to do really is just extend this line backwards right here. The velocity of E is held to be horizontally, so a line perpendicular to that is right there, and so my center of rotation for the second rod is going to be located right here. Now it's a distance h above E, and we don't know what that distance is right now. So just to sum up some arguments that were made here, C1B is perpendicular to the velocity of B, and C1A is perpendicular to the velocity of A, and the velocity of D is perpendicular to the C1D line, and therefore also to the C2D line. So therefore C2E, this line right here, is perpendicular to the velocity of E. Alright, we were given all the dimensions here in millimeters, and the velocity of B is given to us as minus 360 millimeters per second in the I direction. Alright, since we have the centers of rotation here, instantaneous centers of rotation, we can use the velocity of B, which is given to us, and write it as omega AB, a K unit vector crossed into R sub B slash C1. That's this vector that runs from here down to here. And so therefore it's going to have a minus 400 millimeter J. And when you cross K into J, you get a negative I. That negative sign turns into a positive I, and we end up with 400 millimeter omega AB, I equal to minus 360 millimeters per second in the I direction. So therefore omega AB is going to be a negative 0.9 radians per second. The velocity of D then can be calculated with omega AB K crossed into R sub D slash C1. There's a center of rotation, so D slash C1 is a vector that goes from C1 to D, and that's a vector that's minus 150 in the I and minus 200 in the J in millimeters. I'm going to call that equation 1. Then we can also write the velocity of D in terms of omega DE for this rod, and that center of rotation for that rod is there. And when we write that down, we'll have omega DEK crossed into, well, we know that to go from here over to there is a minus 200, it's to D, it's a minus 250 plus 150, or minus 400 millimeters I. And to go downward here, it's H plus 300 to get down to that position. So we know that that is 300 plus H in the negative J direction. There's a negative sign, and there's millimeters, and that's 2. Now we can figure out what H is, or H plus 300, because if you look at your drawing up there, H plus 300, which is this distance right here, divided by that distance, which is 400, is the same thing as this distance right here, which is 200, divided by 150. And so this would lead you to an equation for H being equal to 700 divided by 3, or H plus 300 is equal to 1600 over 3. We can also get that information by if we take 1 and 2 and equate them to each other, and then write out, we get this equation right here, where remember the 1600 here is really H plus 1600 over 3 is H plus 300. And if you look at the J parts alone, you'll find that you can calculate omega DE to be a negative 0.3375 radians per second. And you'd actually do the I parts, you get the same thing. Now, if you'd not calculated H from right here, but just left it as an unknown, then you could have calculated it out of the I parts equation, and you would have gotten the value of H that we got right here. Looks like I've left the units off right there, but it is in millimeters. And then to get the velocity of E, which we asked for the B part, then we do the omega DE. Since the center of rotation is right up there, then we just need that distance right there and omega DE. So we get omega DE, K crossed into H in millimeters minus J then. And that's equal then to omega DE H millimeters times I unit vector. And when you plug in your numbers, you'll end up with a minus 78.75 millimeters per second in the I, or it's a negative I direction.